All right, so I'm not very good at presentations, and it feels like a presentation. So I'll just try to walk through it. So this is my example. This is the code, and I'll run it real quick just so you can see it working for a range of just 100, 100 cycles, I think it is, but it'll spit out the primes for this 100 cycles. And we're getting 28 primes. That's these three minus the 25, or I'm sorry, 28 minus these three is the expected amount, 25 primes in 0 through 100. And it gets a little extra because of what I'm calling an X factor. And the reason that I added the X factor is because for whatever reason, 13 kept disappearing. So I thought, what if I just cycle through this a couple more times based on some data that I'm passing in? And as a result, I'm getting my 13. So watch, I'll take the 13 away, or that X factor away, and I only get the first three primes. If I add 0, I get some of the primes, but once again, the 13 is missing. So I really don't know what this does, even though I wrote it. But this is the cool part. Check this out. This is 9.006 quadrillion, well, almost 9.007 quadrillion. And I'm asking for up to 100. And watch how fast this is. So this isn't all 100 in that quadrillion range, but these are quadrillion levels. And I wrote a library called prime, which does a quick prime number check. And as you can see, sure enough, it is prime. So what's cool is that you can play around with these numbers. You can do 11, 200, or 200. And it will do some really interesting stuff. Like now we're getting primes in the 200 range and the primes in the 100 range. But notice 13 is missing again, but so is 17. So I don't really know what this does, but I know that I need it. Does that make sense? And real quick, let's go take a look at the code so we can see how it works. So this is my prime gen function. This is my little prime checker, which is the same thing that prime with a y uses. And so here's my here's my variables, including the X factor. It defaults to this if you don't pass anything in. And basically it's a while loop. It says while n is less than the passed in z value, which I believe is a cycle. I still don't fully know how my own program works. If it's so while it's less than z, it'll check the first few numbers with my prime checker function, and if they're prime, it'll push them into the array. And then from there, it doesn't use check necessarily. This is the whole algorithm for the most part until it thinks it has a prime, and then it will check it. I think that that's inevitable. It is technically generating the numbers, but it has to check them. And I tried my best to get rid of the check, but I think I'm going to have to use it. So it basically says n plus the previous prime minus the prime just before that plus x factor. And that's pretty much the entire formula if you add the check in as well. By the way, this just says if it's not divisible by 2 and if the length is greater than 3, so you have 2, 3, and 5 as a starting point. No, it's modulus. Well, I should say it's more. There's a formula pi of x. That's what this is. There really are no guarantees when it comes to prime numbers. This is the closest that I was able to find. So most prime numbers can only be identified through prime factorization. And even then, there's some questions according to my research. I'm not a mathematician, so I can't speak much more intelligently about that, but that's what I understand from my research. But what's really cool, remember when I was telling you that I could generate the primes between 1 and a million in like a minute and a half? Well, I've gotten that down to mere seconds. So let's turn this off real quick. Oh, crap, I have to retype that. Less than a second. Pretty cool, huh? Yeah. So it says the total here is 61,085. I'm missing about 18,000, 17 or 18,000. So that's not bad. Now, if I were to tweak my X factor, I could probably find the right combination of numbers to get these other missing numbers. Go ahead. So that would take a tweak to the algorithm, because if here, I'll show you here. We'll console log the algorithm's primes. Notice that I have a sort right here, a set to remove duplicates and a sort. The original array has duplicates in it, and it's out of order. So notice there's two 17s, two 31s, or three 31s, four. Well, yeah, sure. XF, what is that going to be? Oh, yeah, let me do that before the plus plus. Not that it matters. I just like my plus plus at the very end. This is dangerous. Okay. Can barely hear you, Brandon. Cool. Okay. I'm hitting run. Yeah. I had a feeling that this would crash things. Yeah. But you know what? I can escape out of it just fine. That's cool. So it's not crashing that bad. But that is an interesting concept. You know what? Let's lower the range a little bit. Prime dot slice? PRMs dot slice. Oh yeah, this is more like a moving average. I was thinking about leveraging that somehow with this. I want to try it on a smaller range because it may complete, but I have it set to 1,000,000. So let's try 1,000. There we go. So what is my performance on that? 10 milliseconds. No, because we're going beyond the expected range at this point. So let me take this away, and we just use the generated primes. So I guess I have to look it up. How many primes? There are 168, and we have way more than that. So I would have to count. I would have to count from here to 0 to find out if we have all of the primes. Which which is kind of what the generator is all about, is to use previous primes to calculate next primes. So this kind of behavior is sort of expected, especially with the way I wrote my algorithm. But this is better. So now I have some more to play with. So I think that's a great addition. It crashes at 1,000,000, but I'm gonna just comment it out for now. So yeah, so that's my prime number generator. Yeah, thanks for your feedback on it. Yeah, let me stop recording. Oh wait, I forgot how to do it. There we go.